Good morning everyone. Today I am going to present the paper 6 Uniform Maker Baker Game is PSPACE-Complete for STACS 2021. I am MD Lutfar Rahman and my advisor is Dr. Thomas Watson. We are from University of Memphis. Okay. First I would like to introduce CNF Boolean Formula, a type of Boolean formula. Stands for conjunctive normal form. In a CNF formula, it has some ends of some clauses, where clauses are odds of some literals, and the literals are negated or unnegated Boolean variable. In this particular example, this is a 4 CNF since all clauses have at most 4 literals. In general, a WCNF means all clauses have at most W literals. Usual notations for a CNF formula is phi and psi, and a satisfying assignment to a CNF formula happens when all clauses have at least one true literal. An unsatisfying assignment to a CNF formula means some clauses have all false literals. Okay. Before going to the main problem, I would like to introduce two classic problem. One is SAT. SAT stands for satisfiability. The input is a CNF formula phi and the output is does phi have a satisfying assignment or not. This problem is NP-complete problem. In fact, this is the first NP-complete problem back in the 70s. It is very unlikely to have a polynomial time algorithm for this problem. And the second problem is TQBF. TQBF stands for true quantified Boolean formula. The input is the CNF formula phi and its set of variables x0, x1 to xn, and the output is whether there exists a value of x0 for all values of x1, there exists a value of x2 dot 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 till the last variable phi is satisfied or not. This problem turns out to be a PSPACE-Complete problem. It is in fact a lot harder problem than NP-complete problem. Interestingly, this TQBF problem can be considered as a two-person game, and games like Go, Super Mario Bros, Zelda, Checkers, Solitary are a computational equivalent as TQBF. All right. So let's take a look at the game version of TQBF. We call this game ordered CNF game. So the idea is we have two players, player T on the left, player F on the right. So and there is a formula in the middle, CNF formula in the middle, and the rule of the game is player T wants the formula true and the player F wants the formula false, and the game rule is at the beginning player T assigns a value to x0, then player F assigns a value to x1, then they alternatively takes the turn, and the important thing here is the order of the variable is fixed. This is why we call this game ordered CNF game. All right. So let's simulate a game on this formula, and let's see how this game happens. So suppose at the beginning player T will have to assign a value to x0. So suppose player T assigns x0 equal to 1. Now it is player F's turn. Player F will have to play x1 and assign a value. Suppose player F assigns value to x1 equal to 0. So the first clause is satisfied because it has one true literal. Then it is player T's turn. Player T will have to play x2. Suppose player T plays x2 equal to 0. So the last clause is satisfied now. Now it is player F's turn. Player F will have to play x3. Suppose player F plays x3 equal to 0. Now it is player T's turn, and player T will have to play x4. Suppose player T plays x4 equal to 1, and all the clauses are now satisfied. So it does not matter what player F plays for x5, since all the clauses are already satisfied. Now at the end player T wins this game. So, now the question is, who has a winning strategy given a CNF Boolean formula, and how computationally hard it is to decide who? We already know this problem is PSPACE-Complete for 3 CNF. Alright. Now, we study the unordered variant of this CNF game. That is, we have two players, player T on the left and player F on the right. Player T wants the formula true and player F wants the formula false, and the game rule is player T can pick any variable and assign a value, then player F can pick any of the remaining variable and assign a value, and in the end player T wins if the formula is true. So, unlike the ordered version, in the unordered variant of this game we have no intended order. Alright. So, let us simulate the unordered variant of this CNF game on the same Boolean formula. Suppose player T has to pick a variable. Suppose player T picks x0 equal to 1. Player T could have played any of the variable, but suppose player T picked x0 equal to 1. Now it is player F's turn. Player F can play any of the remaining variable from x1 to x5. Suppose player F played x3 equal to 0. Now it is player T's turn. Player T can play any of the remaining variables. Suppose player T plays x5 equal to 1. Now it is player F's turn. Player F can play any of the remaining variables. Suppose player F plays x1 equal to 0. Now it is player T's turn, and if you look at the last two clauses, it has one interesting condition. The condition is, whatever player T plays, player F can make x2 and x4 equal, and if player F can ensure x2 and x4 are equal, then one of the last two clauses will be unsatisfied. So, this becomes the winning strategy for player F. So, let us suppose player T plays x4 equal to 1. Now, player F's strategy is to make them equal. So, player F makes x2 equal to 1 and the last clause become unsatisfied. So, in this particular game, player F wins. So, if we ask the same question, that who has the winning strategy in this game, then that becomes an interesting question, and we will work on that. Okay, all right. We'll go ahead and see the notation of this game. So, the game instance is determined by phi, and phi the CNF formula, and x the set of variables. The general notation for this game is G for game and W for WCNF, and the game on positive CNF, if the game happens on a positive CNF, positive WCNF, then we say G plus W. Well, here is the thing, the positive CNF means when all literals are positive in a CNF formula. Okay. So, phi means WCNF, x means set of Boolean variables in the phi, and player T or player F plays from x in any order. So, the problem is the input is phi and x, CNF formula and set of variable, and output is which player has the winning strategy. So, that is our formal definition of this problem. Alright. So, now we are going to see the problem maker breaker game, the title of this paper. So, the problem definitions are slightly different, but they are very related and very similar. So, we have two players similarly, maker and breaker, breaker on the left, maker on the right. So, and we have a set system. It is a set of subsets. So, breaker wants to save all the subset, and maker wants to take a whole subset. So, that is the rule of this game. So, the game rule is breaker picks any xi, then maker picks an xi, then breaker picks an xi, and so on. And in the end, breaker wins if he picks at least one element in all subset. Alright. So, let us simulate the game on this set system and let us see what happens. So, suppose at the beginning it is breaker's turn. Suppose breaker plays x5, breaker picks x5. So, the first set is saved by breaker. Now, it is maker's turn. Suppose maker plays x1, picks x1. Now, it is breaker's turn. If you look at the second clause, breaker now must play x0, because otherwise maker would pick x0 and win a whole subset. So, breaker picks x0. Now, it is maker's turn. Maker this time picks x3. Now, it is breaker's turn. Now, breaker will have to play x2, otherwise maker will pick x2 and win this third set. So, breaker picks x2. Now, it is maker's turn. Maker, the last variable, picks x4, and in this game maker wins because of the last two variables. All right. So, this is the maker breaker game that is being in the discussion in the paper. Now, if you take a look at these G positive W versus maker breaker game, we argue that these two games are actually same. How do we think about these two games? Why do we think about these two games? We will just show some similarities of different arguments. Suppose game on positive CNF, the notation is G positive W, and the maker breaker game on a positive on a set system where every subset has size W. Okay. Positive W CNF, for an example, we have a positive W CNF here in the and the equivalent set system will look like this. And if you see that a CNF, W CNF and a set system are very similar, a clause becomes a subset and the whole CNF becomes set of subsets. So, a clause becomes a subset, a variable becomes an element in the subset, player F becomes maker, player T becomes breaker. So, from this point onward, we will refer maker breaker game as G positive W game. So, that we will talk about different parameters. All right. So, the history of this game. In 1976, maker breaker game for 11 positive CNF has been proved PSPACE-Complete. In 2005, cards proved that maker breaker game for with 3 positive CNF is in polynomial time under some restriction. In 2018, in our Isaac paper, we proved that maker breaker game for with 2 CNF is in linear time. So, our result here is we have 3 main result. One is theorem 1, G6, G positive 6 is PSPACE-Complete, then G positive 5 is NL hard, and then theorem 3 is G4 is NL hard. Interestingly, any result on G4 positive remains unknown. Okay. All right. So, I would like to discuss our approach to solve theorem 1, and that is G6 positive is PSPACE-Complete. So, in the proof we show that 3 TQBF is reduced to G6 positive. So, suppose we have an instance of 3 TQBF, there exists x2n for all values of x2n minus 1 until the last variable, and we have a 3 CNF like this, and where each F1, F2, F3, Fm, each of them is a clause, and this is end of clauses. All right, and we'll create the instance of G positive 6 game, where phi positive is the positive 6 CNF, and the x will be the set of variables. Two main issues here is we have to solve is TQBF has a negative or positive literals, but G positive 6 has only positive literals. Then the second issue is TQBF has an order of variables, but G positive 6 has no order of variables. All right. So, the first issue is TQBF has both negative and positive literals, but G positive 6 has only positive literals. So, the solution is in the TQBF, if we have one variable xi, then we will create two separate variables xi and xi prime, and the relation will be suppose in TQ3 TQBF we have a negative literals here, then in the G6 positive we will have xi and xi prime on that place. This is the negative literal, but this is not a negative literal, this is a separate variable, but we designed this game in such a way that xi and xi prime gets the opposite value. All right. And the second issue is TQBF has an order of variables, but G6 positive has no order of variables. So, the solution is we have to design some way to force players to follow the intended order from the TQBF, and by force we mean neither player ever gets any advantage by deviating from the intended order. So, if T deviates, we design the clause in such a way that T loses immediately. If F deviates, we design the clause in such a way that T has some strategy such that F loses not immediately, but at the end F loses eventually. All right. So, how do we manage to force players to follow the intended order from TQBF? So, that is the main challenge. So, suppose we have a TQBF round, there exists xi for all values of xi minus 1. This is a TQBF round, and we have to maintain this intended order, and for a make a breaker game we have created 16 variables. We have created 16 variables for this one TQBF round, and in order to force players to play in this intended order that simulates this TQBF round, we created these clauses with 6 clauses. These clauses enforced this intended order, and Schaeffer's designed it with 11 clauses, but we improved it with 6 clauses. That is the main thing happened in with our proof and Schaeffer's proof. Okay. And the second thing is, if F deviates, then F loses not immediately, but eventually. So, how do we do that? We design the clauses in such a way that when F deviates, then T can start a chain reaction which leads to a win at the end. So, the chain reaction of that structure of the clauses looks like this, and this idea came from our recent paper Tractable Unordered 3 CNF game, published in Latin 2020. All right. Then we have theorem 2. Theorem 2 is G5 positive is NL hard. The proof we show that 2 TQBF is reduced to G5 positive. We know 2 TQBF is a well-known NL complete problem. The technique is very similar to 3 TQBF, reduced to G6 positive. Interestingly, G5 positive might not be in NL. it might be even harder than that, so we don't know yet. And we couldn't find any result for G4 positive, but we were able to find a result for G4, and we found that G4 is NL hard. So we show that 2SAT is reducible to G4, and we know 2SAT is a well known NL complete problem. But interestingly, G4 might not be in NL, it might be harder than that, but we don't know yet. And so in the conclusion, we say that this G11 positive that has been proven PSPACE-Complete in 1976. This problem is quite famous problem, and many games has been proved PSPACE-Complete from this G11 positive. And since we have a new tighter bound for this game, so it is possible that other game might consequently get tighter result because of the improvement of the parameter. And G5 positive is NL hard, but it's not clear where it actually belongs. It might be even be PSPACE-Complete, that we yet to figure it out. Any result on G4 positive still remains unknown, but we know G4 is NL hard. We at least know G4 is NL hard. Then G3 positive is conjectured to be in P. Even we also have a conjecture that G3 is conjectured to be in P. So all these unknown questions needs to be resolved. We hope that in future we will be able to solve some of this question and settle this problem. All right, thank you. Thank you for seeing my presentation.